So now we're going to work on the analytical solution to this Schrodinger equation, which corresponds to the case of the harmonic oscillator. And then throughout the coming videos, we're going to partly guess and partly deduce our way to our solution, which is pretty much the procedure you normally encounter when you're trying to solve a differential equation. So before we tackle this differential equation head-on, we're going to do a substitution. So as was expressed by Griffiths, he uses this Greek letter Z. So I'm very bad at drawing this Greek letter. And he's going to let this Greek letter be equal to m omega divided by h bar times x. And then since I'm so bad at drawing this, I'm just going to let this be equal to y. It's going to make my life a lot easier. So now we're going to try to express this equation, this differential equation, in terms of y. So now it's in terms of x. I want to express it in terms of y. So of course we can easily take away the x squared. As you can see from this relationship, you can see that x squared is just equal to h bar divided by m omega y squared. So this part is easy enough. So how do we get rid of this x here in the differential? So first of all, let us just consider the case of d xi dx. So instead of d xi dx, I can also rewrite this as d xi dy dx. So this is just the chain rule. So d xi dy, and dy dx, as you can see from this relationship over here, dy dx is really just equal to the square root of m omega divided by h bar. So we just dump this straight in. So this is an alternative expression for d xi dx. So now we get down to d xi squared dx squared, which is this second derivative over here. So the second derivative of xi, that's just equal to d dx of d xi dx. And then as we found, d xi dx can be expressed as this expression as well. So we can just substitute that in. So we have xi dy m omega divided by h bar. And then this is just a constant, so we can just pull this out. And then we're going to use the chain rule again. So instead of d dx, I'm going to write d dy of d xi dy. And then because of the chain rule, I'm going to multiply this by dy dx. And as we've mentioned before, dy dx is really just equal to square root of m omega divided by h bar. So I could just square this actually. So we have two of these square root of m omega divided by h bar terms. So you see that in the end we know that d squared xi dx squared is actually equal to m omega divided by h bar times d squared xi dy squared. So this is how we're going to do the substitution. How we're going to replace this term so that it becomes in terms of y. So now we can just substitute this right back into this expression over here. So the Schrodinger equation, it becomes negative h bar squared divided by 2m, and then for the d squared xi dx squared, we're just going to substitute this straight into the differential equation. And then we have plus 1/2 m omega squared, and then for the x squared, we're just going to substitute this in. So h bar divided by m omega times the y squared, and don't forget the xi. And then on the right hand side we just have this constant e times xi. So now all that's left is really just a bit of simple mathematics. We just need to arrange this into a nicer form. So you see that these constants, they cancel out, which is always a good thing. So if you'll notice that these two constants here are actually the same, so we can just bring them over to the other side to simplify this a bit more. So essentially I'm going to multiply both sides by negative 2 divided by h bar omega. So I'm going to multiply both sides by this constant. So of course here it just becomes 1. You can see the constants, they all cancel out. So I have d squared xi dy squared. And then here you see that 2's cancel out, the h bar omegas, they cancel out, so I get negative y squared xi. And then over here I get negative 2e divided by h bar omega xi. So now we can just rearrange this by one more step. So we have this second derivative, this is equal to y squared minus 2e divided by h bar omega. So times xi. So this is going to be the alternative expression of the Schrodinger equation that we're going to work on in the subsequent videos. So this is actually the same differential equation as this one over here. The only difference is that now it is in terms of y, and don't forget y is defined by this expression over here. So in the subsequent videos, we are going to work on this expression.